We're going to do chapter 6. What's that? Chapter 6? Not there yet. It's going to be up there this week, today or tomorrow. Oh. Yes, but I would, if you want to do chapter 4 and 5, but we won't cover that until next week. So normal distribution, what does that mean? By normal distribution, we're saying that the data is normally distributed about the mean. That's what it tells us. And if it's really a perfectly normally distributed, then the mean, median, and mode are all about the same point. Everything is centered around the middle of the data. And on both sides, we have standard deviations. So there's one standard deviation, there's two standard deviations. So what is this stuff? Why is this stuff important? Because depending on the number of data points you have in your sample, the more data samples that you have, the more smooth your curve is going to be. And in other words, what I'm saying here is if you just took 5 or 6 samples and it didn't come out to be perfectly symmetric, like a normally distributed curve, if you take more and more samples, maybe if the study is true, if it's truly a bell-shaped curve, the data is, it'll come out the more data sets that you have. So that's what we're looking at there. What does skewness mean? What does skewness mean? What does to be skewed mean? Yeah, it's the data is favored or pushed to one side. So now when that happens, we have two possibilities. So in this first one, what skewed is that? Is it positive or negative skewed? What's that? So it's just like the worst favor, the left is always going to right one. Right. Yeah. So this is left skewed. This is right skewed. How can we tell? Why do we call this left skewed and this right skewed? I told you about this a week ago. How do you determine these? And I put them this way for a reason. There's something much easier than it's, you have nothing to memorize, really. Look at your feet. On your left foot, where's your big toe? Is it to the left or to the right of the foot? This is your left foot. This is your right foot because your big toe is here. So that's how you determine. So if it's left skewed, it's negative. If it's right skewed, it's positive. Back opposites. So let's see if I can. Oh, so now a couple things happen. So as opposed to this one, if it's normally distributed, mean, median, mode, everything's in the middle. What happens if it's negatively skewed? If it's skewed left, what happens to it? What happens here? The mean, the median, and the mode. The mode is always going to be the highest point. Now, if it's negatively skewed or left skewed, the mean will be to the left of everything else. So the mean is less than the median, which is less than the mode. Conversely, so it's going to be to the left of it. That's what I mean by less than. So the mean's to the left of the median, the left of the mode. The mode is to the left of the median, to the left of the mode, or the mean. Why is that? Why do you have to know these? Because are you always going to draw a graph? Nope. But if you look at your values, just by looking at the values now, you know what the graph's going to look like. So the mean is smaller than the median, or smaller than the mode. We know this graph will look like this because of this scenario. That's why knowing those is very important. Let's see an example here. So when we create the bell curve, how do we get it? We know by looking at the mean, median, mode, we can define the bell curve. How does this relate to what we just talked about in percentiles and quartiles and deciles? What's that? In a sense, instead of more popular in progress, what you're looking at now, like in percentiles, is how much is this value larger than? So if this was a perfectly normally distributed curve, how much of the data is to the left of one standard deviation? How would you find that out? Well, what do we know so far about bell curves? How many standard deviations are there in a bell curve? You have one standard deviations on both sides. You have two standard deviations on both sides. You have three standard deviations on both sides. Okay, what do we know about these standard deviations? What do we know about one standard deviation? What's that? No, that's that's not, again, you're just describing what it is, not what we know about it. You're just describing what it is. What do we know about one standard deviation? How does it relate to the question I'm asking you here? I want to know what percent of the data is to the left of one standard deviation. How does that relate to this? What do we know about one standard deviation? No, not Q1. But what do we know about one standard deviation? How much data is in there? 68%. We know that. We've discussed it about 4 or 5 times already. We also know how much of the data is to the left of the mean. This takes no math whatsoever. How much is to 1/2 of it? Yeah, obviously, duh. It's a no-brainer. It's 50%. So there's 50%. So we have to know how much is in here. How does this relate to what we have here? How can we figure out an answer here? By, and get what? So where's 34 go? Very good. So here's my mean, one standard deviation. So I know there's 34% of the data there. So how much is less than one standard deviation? So how much is here? No, even easier. Would I just take 50 and add 34 to it? So 84% of my data is below my one standard deviation. How much is in here? Well, you guys are so lucky we don't have in-class exams. I tell you that much right now. This is in the middle. So we know how much is over here total. It's half. 50. 50 is half. So how much is in one standard deviation? This 1/2 here. That's 34. So how much is left over? Very good. So this is 16% in here. So that tells us that 16% of the data falls to the left of one standard deviation to the left. That is how you have to start looking at these things. Yeah, I can do that. Oh, actually, yes. Because what we're going to do here, here's your mean. So how much area is between there? No. So actually, we have to look at first. We have to break down. We had the bell curve here originally. We know we have one standard deviation here. And that has to be 68% of my data. As you said earlier, This is 34%. That's 34%. 2 standard deviations is how much? Approximately 95%. So since this is 95% from here to here, how much is in each half? How much is in here and how much is in here? $47.5 because half of 95. So if this half is 47.5 and this is 34%, how much is in here? Subtract 13.5. So this is 34%. This is 13.5. So I'm going from here to here. So how many percent is that? We have 34, 34, and 13.5. This is 68 plus 13.5. No, 64, I'm sorry, 68%. That makes it 81.5%. Is it really this difficult? You're not sure, or you're just not taking time thinking about it. Because when I asked you how much is in this half, you all gave up. Well, when you're thinking, when somebody says half, there's zero thinking. Half is 50. Now, the reason I'm saying this is because now how does this relate to what we've been doing all along? What if I wanted to know what if I wanted to know this value here, at that value there? There has to be a way we can convert now from these X values to something else that deals with percentages. That's where the Z-score comes in. Remember the Z-score? X minus X bar over S. How does that relate to what we're doing here? Well, first off, when we deal with Z-scores, if it's perfectly distributed, we no longer have a mean. Because the mean could be any number. It could be like 48. It could be any number. But when we convert it to the Z-score, what if my X bar, the mean was 48, and my X was 48, what is my Z value? It's 0. So at the middle, what this is your X and your X bar are equal. So now, because Z is 0, anything to the right is positive, anything to the left is negative. So let's say my X value I'm looking for is 30, my X bar is 40, and my standard deviation is 5. So here's my X bar is 40. My standard deviations to the left, what would this value be? If it's one standard deviation to the left, what would this value be? 35. because you're subtracting 5 from each step. This one would be 30. This one would be 25. One standard deviation is 5 points each step. What would it be on the other side? 45, 50, and 55. So I want to know how much is less than 30. So what I would do, I'd convert this score to a z-score first. 30 minus 40 over 5. Negative 10 over 5 is negative 2.0. That's where this chart comes in, which I gave you in the very back of your packet. These show us the percentages of the area to the right or to the left of a value. So you see in the bottom, if your z value is to the right of the mean, what you'll do is your z values will always be in 2 decimal places. So in this one, we want to know what is the to the left of negative 2.00. So we go to negative 2 here. This is the first decimal. Here's the second decimal. So it tells us that 0.0228. So it says that 0.0228 or 2.28% of the data is to the left of this number. That's how this works. So here your z values are found on the left and the second decimal is over here on top. You don't need your phone. I'll tell you when it's, and you have no classes today, so. So what is the z value of 2.43? Is that to the right or to the left of the mean? And since it's positive, it's to the right. So it's 2.43. So it'll tell me what is the area, the percentage of the numbers to the left of it. So I go to 2.4 and then go to 0, 1, 2, 3. It's 0.9925. So it tells me that this area here is 0.9925 or 99.25% of my data falls to the left of that z-score. So what if I have 1.99? What percent of the data falls to the left of it? Very good. Or 97.6% of the data. How much percent falls to the right of it? How much is the whole thing? How many percent? 100%. So if I subtract what I don't want, which is subtract the 97.67, what do I have left? 2.33. What's that?
97.
Well, 97 plus 3 is 100, but it's no longer 3 because I have a 0.67. So it's going to be always one less than this. It's always one less than this one. Yeah, so we'll do some more problems with these because I gave you a whole bunch of problems that we can look at here. We'll do that on next week. But this is the reason why now we can look at, I give you any data point, as long as you know the mean and deviation, you can see what is your, how big is that compared to everything else. No, we don't have to go to percentiles or deciles or quartiles. We can now pick anything. And not only that, but we're not restricted. I can give you two numbers. This is, let's say it's negative 1.01, and this is positive 0.92. What is the area between there? How would you find it? Well, take the bigger one. The chart gives you that area. This one gives you this area. So let's call this A and call this B. So A minus B would be what's in there. It's a new way of thinking of things. And this is the way we do it in statistics, so we can calculate percentages and probabilities. All right. Happy Thanksgiving, everybody. And you're thinking, God, finally he's finished talking.